Greetings, differential equation scholars, and welcome to the first video in a sequence of videos covering applications of second-order differential equations. In section 5.1, we start out by looking at problems of motion, in particular, the motion of objects attached to springs. And so here we have a problem, you'll see on my graffiti-covered screen, that says that we've got an object. It weighs 6 pounds. And it's known to stretch a spring by 8 inches. But suppose we take that object and we move it up to a position that is 1.5 feet above its equilibrium point, and then we release it from rest. We want to know what the equation of motion for the object is going to be. In other words, we want to try to predict where it will be at various times t after we've done that, given what we know about the system. Then in the end, we're going to answer the question, what is the period for the motion, which will describe how long it takes for the object to complete one full cycle of its motion. To understand this problem, we first have to have some common understanding about what our variables are and what our frame of reference is. So you'll see over here on the right-hand side of the screen, we have a diagram of the spring and the object that's attached to it. You notice that right here we've got the equilibrium point. This would be the place where if the object was just hanging from the spring, where it would naturally be at rest. We're going to take that point there to be x equal to 0. We're going to be using x as the measurement of the displacement of the object from equilibrium. Now, an important point of understanding here, and you'll see this on the diagram, is that positive x values represent displacements below equilibrium, that is closer to the ground. So as the object is moving down away from the equilibrium point, the x is increasing. That means if we push the object up above its equilibrium point, it will actually have negative x values. So if the object is starting at 1.5 feet above its equilibrium point, it's actually starting at a point here that would be x equal to negative 1.5. So that's our understanding about our coordinate system here. X is going to represent the position of the object at any given time. Positive x's mean below equilibrium, negative x's mean above equilibrium. We want to find an equation for that x. Now, to be able to do that, we first have to understand something about the spring that the object is attached to. You may remember from Calculus 1 or 2 that springs obey something called Hooke's law, which says that the force needed to displace a given spring by a distance of s is equal to k times s, where k is what we call the spring constant. So in other words, the force is proportional to the displacement, and k is that constant of proportionality. Well, if we're going to solve this problem, we need to know what that constant of proportionality is for the spring in our system. Now here we were told that 6 pounds, and that's going to be the force in pounds, displaces the object 8 inches. Now, in our English system, we usually use feet as our common unit of measurement. So 8 inches would be 8/12 or 2/3 of a foot. When we substitute those into Hooke's law, we're going to get that 6 is k times 8/12, and then that ends up telling us that k is equal to 9 pounds per foot. That's our spring constant. And we need to know that to proceed onward with the problem. So now we know the spring constant is 9 pounds per foot. That's our k value. And so where do we go from there? Well, the next place that we're going to go from there is to come up with a differential equation. So on my second graffiti covered screen here, you'll see how we're going to do that. We already know the k value. Another value that's important for us to know here is the mass of the object. We knew earlier, we were told that the object weighed 6 pounds, but that's not the mass. According to Newton's law, F is equal to ma. And so the mass is actually the weight divided by acceleration due to gravity. So here that's going to be 6 divided by 32, or 3/16. Um, and in the English units, we refer to this uh, pounds times seconds squared divided by feet as a slug. So we have 3/16 of a slug is the mass of that object that's attached to the spring. Now that we know our K value, the spring constant, and we know our M value, which is the mass of the object that's connected to the spring, we have everything that we need to form the differential equation of motion. Um, Newton's law would say that any given time, the force of gravity that is pulling down on the object, which is m times g, would have to be the same thing, kind of equal out or balance out the force that is being applied by the spring to try to return the system to equilibrium. Your book does a very nice job of showing that when we resolve these two forces, when we bring into being both the gravity pulling down and also the restorative force of the spring pulling back up, that we get a differential equation that is m times a, or m times second derivative of x, plus kx equal to 0. So we have one force here. This is a force being exerted by gravity. And we have another force here, which is coming from essentially from Hooke's law. And the sum of those two opposing forces has to be 0 at any given time for our free body diagram. So we have m times second derivative of x plus k times x equals 0. And for what we call ideal undamped motion, which is what we're looking at today, that is our starting point. M times second derivative of x plus k times x equals 0. Now, another way to write that equation is if we divide by m, we could say that the second derivative of x plus k over mx is equal to 0. So here's another alternate way of writing that same equation. And you'll notice here that the expression k over m has been written as omega squared. This is a convention here, the reason for which will become apparent in a minute. But either one of these is a good way of starting with our equation of motion. If we substitute in m equal to 3/16 and k equal to 9, which we found earlier, one way of writing the equation is 3/16 x double prime plus 9x equals 0. If we normalize that by dividing by 3/16, that's going to give us an alternate form of the equation of x double prime plus 48x equal to 0. So these two equations are the same. This one right here is the one that we would typically use as we are going to look for the solutions to the differential equation, that normalized form with the leading coefficient of 1. So we've learned how to do that. That's what chapter 4 is all about. Everyone here knows how to solve this second order linear differential equation with constant coefficients. When we go to do that, as we come up with our general solution, here she is. All right. We know that x double prime plus 48x equal to 0 has a, whoops, almost wrote over it there. But we know that that has a auxiliary equation, here it is, of m squared plus 48 equal to 0. That's the auxiliary equation that goes along with this differential equation. What are its solutions? Well, it's going to have two complex roots. M is equal to plus or minus the square root of negative 48. but the square root of negative 48 is 4 times root 3I. And that means because we have these two purely imaginary roots to the auxiliary equation, what are our solutions going to be? Well, they're not going to be exponentials. They're going to be sines and cosines. In particular, we're going to have the cosine of 4 root 3t and the sine of 4 root 3t. Those are our y1 and our y2. So our general solution from our theory from chapter 4 is a linear combination of those two. C1 times the cosine of 4 root 3t plus C2 times the sine of 4 root 3t. That's our general solution for our equation of motion. Now that we've got that general solution, though, we want to make it a bit more particular. We did have some initial conditions that we had. So now let's go and apply those initial conditions to find out where those would take us. Here's our screen showing our initial conditions, our fourth graffiti screen. I hope you've been enjoying my graffiti. What are the initial conditions? We were told two things about this system: an initial position, which was 1.5 feet above equilibrium, and we were also told that the object was going to be released from rest. Well, those two things translate into two initial conditions. The fact that it's released from a position that's 1.5 feet above the equilibrium, remember we said earlier that that means that our initial position, which we would call x sub 0 here, our x sub 0, trying to do a little underline there, our x sub 0 has to be negative 1.5. Also, we were told that it was released from rest. Released from rest means there's no initial velocity. We're not pushing up on the object, we're not pulling down on it, we're just releasing it from that position. So x prime sub 0, the initial velocity, is 0. We've got these two initial conditions, and now we want to see where they take us if we apply them to our general solution that we had obtained in the previous slide. So when we apply x of 0 equal to negative 1.5 and x prime of 0 equal to 0, what can we now conclude from that? Well, we can get our final form by just doing a little bit of algebra. If we know that x sub 0 is equal to negative 1.5, well, what was the original form? The original form was C1 times a cosine plus C2 times a sine. When we substitute in 0 for t, we're going to be taking cosine of 0 and sine of 0. But sine of 0 is equal to 0, and that's going to make this term go away. So we'll just have that C1 times 1 equals negative 1.5. So that coefficient C1 has to be negative 1.5. When we take the derivative of our general solution, x prime of t, we're going to get this expression here, negative 4/3 C1 times the sine of 4 root 3t plus 4 root 3 C2 times the cosine of 4 root 3t. That's our first derivative. If we evaluate that at 0, this term here is going to go away, the sine term. We'll only be left with the cosine term again because the cosine of 0 is 1. And that'll tell me that 4 root 3 times C2 has to equal what? It has to equal 0. But that means that C2 is 0. So even though our general solution was a linear combination of sines and cosines, and in general class you should expect that most of the time your equation of motion for this situation of what we call idealized undamped motion, we're not taking into account any forces other than gravity or the force of the spring. if we only take those two things into account, we don't take into account friction or any of the other good things that probably really happen in life. In general, your solution is going to be a linear combination of sines and cosines. In this particular case, though, the sine piece goes away because of the fact that we had we're releasing the object from motion, from rest. The fact that there was a zero initial velocity dictated that C2 had to be zero. So we're left with only a cosine term. And our final form for the equation of motion will be -1.5, which is our C1, times the cosine of 4 root 3t. So we could use this formula to predict at any time t exactly where that object is going to be in our system. So we've completed the first objective, the primary objective, which was to find our equation of motion. But there was one additional question that we posed, you might remember at the very beginning, which was, what is the period of motion? Yes, we know how to predict where the object will be at any given time, but how long, for example, does it take for this object that we move to -1.5 feet above equilibrium? When we release it, it's going to go down, and then the spring is going to bring it back up. How long does it take to go from 1.5 feet above equilibrium down to the bottom and then back up again? That period, that amount of time is referred to as the period of motion. And because of the fact that it's periodic using sines and cosines, and because the sine and cosine functions have periods of 2 pi, it turns out that we can derive that the number of seconds needed for an object in idealized undamped motion to complete one full period is going to be, we use the letter t for it, for the period, capital T, and it's going to be simply 2 pi divided by omega. Now you might remember omega from earlier. Omega squared was the coefficient of x in our differential equation that was normalized. That was 48 for us. 48 was the quotient of k divided by m. And so that's what we call omega squared, is 48. And that means that omega is the square root of 48, or 4 times the square root of 3. The formula says that your period will always be 2 pi divided by that omega value. So in this case, it's going to be 2 pi divided by 4 times the square root of 3. Or pi divided by 2 times the square root of 3. 2 times the square root of 3 is about 3.4. It's a little bit, just slightly more than pi. So when we take that ratio, pi divided by 2 root 3, we're going to get a number that's just a little bit below 1, 0.907 approximately. And that is the period, that's the number of seconds that it will take for this object to move from its highest point, which was 1.5 feet above equilibrium, and go down and return back to that initial point. Incidentally, the distance, the maximum distance that the object can move from equilibrium to its either its highest point or its lowest point, is called the amplitude of motion. Here, that's going to be 1.5 feet. In a future video, we'll take a look at computing amplitude when we have a sum of sines and cosines. But here, what we would refer to as the amplitude of motion is 1.5 feet, and that's the maximum displacement of the object from equilibrium at any point in time. So there's our first problem, dealing with section 5.1.1 with undamped idealized spring motion. In future videos, we're going to start to introduce some other factors that might come into play, such as, say, friction that might damp our motion. Or maybe there's some driving force. Maybe in addition to the initial force that might be applied to the object, maybe there's some constant force that's being applied to the object in addition to gravity and the spring. So we'll take a look at those other possible features that could factor into the motion and how they change our solutions. in upcoming videos. But I hope this has been instructive, and look forward to another video coming out tomorrow dealing with spring motion and applications of solutions of the second derivative.